Go.
Okay, so our presentation is on cross-cutting relationships. Now, Rugre will go into more detail into what cross-cutting relationships are.
Okay, so basically cross-cutting relationships are just about finding out the age of the rock where you can't do radiometric dating or look for fossils or anything like that, where it's just too difficult to do that. So basically geologists look for folds and unconformities and stuff like that to work out the history of the area. So basically this is just a model of like an example of how you could use conformities to work out the age of the rock. And basically this diagram shows how geologists use conformities. So there's bed 1, 2, 3, and 4. There's a fault going through bed 2, so that means the fault is younger than both, all 3 of these beds. But there's like a plane of unconformity running across here, so that's younger than all the features on here. So basically that's what cross-cutting relationships are.
Okay, now we've got a part where you're recognising strike-slip faults. Strike-slip faults are easy to identify. It's when they are displaced from the bed. However, you can't be specific as to where dip-slip faults occur from. Strike-slip faults are usually along the horizon of the fault, and two pieces of information are needed. One is that if the actual plane of the fault is displaced, then the movement must be horizontal, and dikes can also be exposed that way. The second piece of information is if the outcrop width of the beds on either side of the fault is the same, then no vertical movement has taken place. As you can see from this picture, the fault is there and there's displacement on either side. This image shows the strike-slip faults in a simpler form. As you can see, the movement is along the horizon and it's to the left. At the bottom, it's also to the horizon, but to the left. Sorry, the top was to the right. Once again, there is no vertical movement. Strike-slip faults must always be along the horizon. Determining up-throw and down-throw faults on a map. In rocks on maps, the youngest rock is always on the top, oldest being at the bottom. New rock is always exposed at the top. It can be a much complicated task to identify the age if folding has taken place. Here we have a 3D model. If the top of the rock was to be exposed, down-throw fault would take place. As you can see, the new rock would form there. This is how you identify faults in a map. The top is isometrical anticline. The limbs will separate from each other and the outcrop will be produced by shallow dip. It's displaced by a strike-slip fault. This middle picture shows a symmetrical syncline where the limbs are the same width being there and they're displaced by dip-slip faults. Down throws to the west, outcrops further apart on the western side, which is there. The isometrical anticline are when the limbs are different widths, so you can tell they're different widths, and it's displaced by a dip-slip fault. The down throw is once again to the west, and the outcrops are closer together.
Okay, so basically on this slide, the cross-cutting feature on here is the dike exposed to the surface here, so we know that that's going to be the youngest feature of the whole rock, and obviously the bottom ones are the oldest, and then they get younger as you go to the top. And yeah, this is just showing the same thing again. Bottom rock is the oldest and youngest rock at the top.
We hope you understand cross-cutting relationships from our presentations. Thank you for watching.
How good was that?